office hours if you want to say hello. Yeah. So this week you have a lot of work because you have a lab report on Wednesday, which is tomorrow, and a fairly long problem set involving collisions of various sorts. So yeah, so on that note, we need to go to what we were doing. We started collisions last week. So right, so let me remind you what we did last time. We took some kind of a mass, another mass. I don't know where that came from. And then here's M1 and here's M2. And we had an initial velocity for M1 and an initial velocity for M2, which we set to 0. And these don't have to have the same masses. And we were doing this all in 1D. So this was a collision in 1D, and it was elastic. So elastic means energy is conserved, and momentum is always conserved. The collision itself involves interaction between the two masses, and so it doesn't affect the center of mass motion or the total momentum. So the momentum is conserved. So you have two conserved quantities if it's an elastic collision. So momentum, that's the total momentum. And in this case, it's the kinetic energy because it's not a relativistic collision. Kinetic energy are conserved. And we assumed that we have the initial velocities for both objects and we have their masses. And what we want to find out is the final velocities. So, so in 1D, we have one momentum conservation equation, and then we have this kinetic energy equation. So we have two equations, and our two unknowns are the final velocity for M1 and the final velocity for M2. And so we could solve for both of those using these two equations. So we have two equations and two unknowns. And that meant we could solve for the final velocities. So in this particular collision, this is not F. This was initial. Oops, come on, erase. 2I. Those were the initial velocities. So with the initial velocity of M2 being 0, when we use the momentum equation and the kinetic energy equation, setting the initial to the final ones, we solve for the final velocities for both objects, and this is what we got. V1F is equal to M1 minus M2 over M1 plus M2 times the initial velocity and the final velocity for the second object was this times V1I. And so what we were about to do at the end of lecture last time was compute some limits. So the first limit I want to compute is what if M2 is a lot bigger than M1? So the limit of M2 over M1 goes to, that's the same thing as saying M2 over M1 goes to infinity of V1F. So M2 is much, much bigger than M1. And so the M1s drop out of this equation. And so this is equal to minus V1I. So when M2 is really big, M1 just bounces right back. It has the same velocity as it goes in, except with the opposite sign. And so M1 just does this. So let's compute the limit for the other one. V2F. And now looking up here, M2 is really, really big. And so this goes to 0. And so, so this is M1, whereas M2 just doesn't move. So it's kind of like M1 just bounces right back, and M2 is like a brick wall. It just doesn't move because it's really massive. It's kind of what you expect. So let's do another limit. Erase these guys. It's helpful to keep the, let's look at what if M1 equals M2. So if M1 equals M2, then V1F, so looking at the top equation here, is equal to 0. And V2F, we have, now looking at this one now, we have 2 divided by 2 is equal to V1I. So what's that mean? So we have this guy comes in, and then afterwards, the first one is fixed. So it just sits there, and then this guy leaves. So what's this? This is like, I think the picture, what did we derive the topmost equations from? Oh yeah, so to remind you, last week what we did is we wrote down the formula for momentum before and after the collision, and it has to be the same. Momentum has to be conserved. And then because it's an elastic collision, we wrote down the condition for conservation of kinetic energy. And then we use those two equations to solve for the final velocities. So that's where those two equations came from. So we derived those last lecture, and they're in the lecture notes. So the derivation you can follow in the lecture. It's a little bit of arithmetic. It's not a lot of arithmetic. So right. So the picture that I want you guys to think of is the Newton's cradle picture. So if I pull this guy, well, let's just do another one. If you pull this guy out, then it hits this one, and then this one hits that one, and this one stops, right? And then this one hits that one, then this one with the same velocity, and then there's consecutive collisions, and then the last one comes out with the velocity of the initial one. So if you guys ever seen the Newton's cradle, a little, demonstration. So what's not intuitive about the Newton's cradle demonstration is you have to actually think about these as consecutive collisions. So what if we had, if these two were stuck together, or what if if we had 4 of these stuck together? Then if we go back to these equations, so instead of having this limit where the velocity of the first one winds up at 0 and the velocity of the second one just comes out with the same velocity of the first one, then instead M2 would be bigger than M1, and so you would get a different velocity. So you wouldn't. So when you look at Newton's cradle, you have to, if you look at it really carefully, what you'll notice is there's a little bit of space between each of these balls when it's at rest. And the reason there's a little bit of space is to make sure they're not actually touching during the collision, because if they were all touching, then this would act like a single large mass, and you wouldn't have the last one pop out. So Newton's cradle is kind of sneaky in that it's set up so that you have a series of consecutive collisions, each one conserving momentum separately. So a little bit of subtlety in that. Okay, so let's get back. One of the things that it's really handy to do is to know how to do collisions in different reference frames. And so I'm going to talk about, so we had the example that we had before, where we have 2 masses, and this one is fixed, and this is V2I is not fixed. I'm going to call this the lab frame. And now I'm going to redo this collision, but we're going to work in the center of mass frame. So we're going to define a new set of velocities, 2u2, I don't want to do 2, I want to do 1, u1i, u1f, u2i, u2f. And these are velocities in the center of mass frame. So how do you relate velocities in the lab frame to the center of mass frame? So so u1i is equal to v1i minus the center of mass velocity. Center of mass velocity doesn't change during the collision, it stays the same. So you know, so you can convert back and forth. So, and likewise, u2i is equal to v2i minus v center of mass, and the same for the final velocities. So this is how to get into the center of mass frame. And the inverse transform, you just move the center of mass velocity to the other side of the equation. And so v1i is equal to u1i plus v center of mass. And likewise, v2i is equal to u2i plus v center of mass. So this is how to go from the center of mass frame to back to the lab frame. And we can do the same thing for the final velocities too. So there's nothing, you know, I just wrote it down for the initial ones, but we can also do the final velocities. Okay, so let's solve the problem in the center of mass frame. So we can compute the center of mass. And so what does conservation of momentum look like in the center of mass frame? Well, the total momentum in the center of mass frame is equal to the velocity of the center of mass, which is 0 by definition, because we're in the center of mass frame. So m1 u1i plus m2 u2i is equal to 0. And so this is the total momentum. And likewise, we can write the same expression, but for the final velocities. m2u2f. So what about the kinetic energy? Well, a couple lectures ago, we showed that you could always write the kinetic energy as a translational part plus a relative part. So in the center of mass frame, the translational part, which is the center of mass kinetic energy, is 0. And so the kinetic energy we can write like this. Actually, why did I do F? Let's do initials. u1i minus 2 u2i squared. So what's this? This is the velocity difference. And this is the reduced mass. So remember the reduced mass. So you can only do this for the two-body problem, but this is a collision between two bodies. So we might as well write the relative kinetic energy in this form where it depends on the reduced mass times the velocity difference squared. So the reduced mass is this. So this is the initial kinetic energy, and if it's an elastic collision, then that's equal to the final kinetic energy, which we can write like this. So 1F minus, that looks like a 2, and I meant it to look like a 1, minus 2F squared. So, so what's the collision look like in the center of mass frame? So let's draw a little picture. We've got it coming in, and then because we're in the center of mass frame, if this guy is bigger, it has to have a lower velocity in the center of mass frame. Then they collide. And so what we're going to show is that this guy has to completely rebound at the same velocity, and this guy has to completely rebound at the same velocity in the center mass frame. So let's show that. So that this is only for elastic collision. You get complete rebound. So so looking at this equation, we can always write U2I in terms of U1I. And so let's do that. U2I is equal to minus M1 over M2 U1I. And likewise, I can do that for U2F. That just comes from the, why is the relative kinetic energy conserved? The relative kinetic energy is conserved if we have an elastic collision. So there's no energy lost if you have an elastic collision. So in the center mass frame, the translational kinetic energy is 0. So if we conserve kinetic energy, it means the relative kinetic energy has to be the same before and after the collision. That's why. So we're doing an elastic collision example. Okay, good. So we can take these expressions and stick them in there. And when you do that, you get 1 plus, so if I just stick this in here, I get 1 plus M1 over M2 squared U1I squared is equal to the same thing, 1 plus M1 over M2 squared is equal to U1F squared. And so these things cancel, and you wind up with the magnitude of the initial velocity has to be the same as the magnitude of the final velocity. And they're, either they could be the same, at which point the two masses would have passed through each other, which is unphysical, or they have to flip. And so that means U1I has to equal minus U2 U1F. So the initial velocity has to equal the final velocity, but with the sign flipped. And so using this expression instead and putting it in here, we can find the same result for the other mass. And so in the solution now is like, meaning what did we find for the final velocities in terms of the initial velocities is this. U1F is equal to minus U1I, and U2F is equal to minus U2I. So the velocities just flip. So if I have these two guys like this, they just turn around with the same velocities. So that, makes it really pretty easy to find a solution, right? If you go into the center mass frame, you just know that you have to flip them. And then if you want, you can then go transfer back into the lab frame. So let's do that. So, right, so V1F is going to be equal to U1F plus the center of mass velocity. So the center of mass velocity, let's compute the center of mass velocity, is equal to 1 over M1 plus M2 times M1 V1I plus M2 V2I. For this problem, we assumed that the initial velocity of the second one was 0. This was assumed. And so this is equal to M1 over M1 plus M2 times V1I. And so now we can calculate the final velocity of the first one. So this is going to be minus U1I because the center of mass velocity flips. And right, okay. So we also have to know what U1I is. So let's figure out what U1I is. U1I is equal to V1I minus the center of mass velocity. And so if I compute that, it winds up looking like this. M2 times V1I. That follows from sticking this in here. Then now let's compute the final velocity. So this is plus the center of mass velocity. So this is equal to m2 over m1 plus m2, taking this times v1 plus the center of mass velocity, which looks like this. This is an m here, m2, v1I. So when I add these two guys together, I get this m1 minus m2 over m1 plus m2 times v1I. Okay, that felt like a lot of arithmetic, but if you remember, this is what we calculated before. So what did I do? What I showed you is that you can do the calculation either in the lab frame, or you can do it in the center of mass frame and flip back and forth into the center of mass and back out again. So the two are equivalent. You get the same answer, or you should get the same answer. If you didn't get the same answer, you made a mistake. So that means, yeah. So sometimes it's a lot easier to solve the problem in the center of mass frame. So in particular, for this particular elastic collision, velocities just flip in the center of mass frame. So it might be faster to solve the problem in the center of mass frame and take the time to go in and out of the center of mass frame, rather than trying to solve a more complicated set of equations in the lab frame. So that's kind of the point of this exercise. So qualitatively, what do we mean by, so this is kind of one of these things, when talking about reference frame, you'll hear this over and over again in, especially when you start to learn more about special relativity. And the idea is the laws of physics shouldn't depend on the velocity of the observer. And so when we say energy is conserved or momentum is conserved, I'm looking at a lab experiment. So think about if you're sitting in a train and you're looking through a window at another train, it's at night, but you don't know what the other train moving and you don't know what you're moving, but you could look at that collision and you might see it as if it were in the center of mass frame, like these two particles approaching each other and bouncing off each other, or you might see one coming in and bouncing off the other. Independent of what frame you're in or they're in, the laws of physics should be the same. And that means total momentum should be conserved and total energy should be conserved. So that's kind of the point. So this principle of relativity, laws of physics shouldn't depend on just the velocity you happen to be moving at, or the experiment happens to be moving. Okay, so far we talked about elastic collisions. So now let's talk about anelastic collision. So what about non-elastic collision? So we have two particles again, and momentum's always conserved, but that only gives us one constraint. So if we have two particles, that gives us two initial velocities. We want to find two final velocities. So if energy is lost, you need to know how much energy is lost in order to figure out what the final velocities are. So yeah, otherwise you can't solve it. But one type of problem that you can solve is like, what if the two particles stick together? So let's do that. Two particles stick together. So here's the setting. Now we have another particle. And this is m1 again. It has some initial velocity, v1I. And this is m2. And it has an initial velocity, v2I, which will set to be 0. So this is going to be a lab frame. Then afterwards, they stick together. And they move at a single velocity, which has to be the center mass velocity, because momentum is always conserved. So the final velocity has to equal the center mass velocity. And so we can figure out what that is just by, computing it. Like that. So and there would be another term here, except that we set v2I to be 0, and so that other term drops out. So Right. So this is the final velocity for, the stuck together particles. So what's the final kinetic energy? So the kinetic energy, the initial kinetic energy. So now we have a different initial kinetic energy than the final kinetic energy because it's not an elastic collision. So the initial kinetic energy is easy to compute. It just depends on this guy because the M2 is fixed, so it doesn't have any kinetic energy. So that's the initial kinetic energy. So this is initial kinetic energy. So what about the final kinetic energy? The final kinetic energy is just the total mass times the center of mass velocity squared. And so we can calculate that if we want. And then we put in the center of mass velocity squared. And we could write this a little bit more simply like this. That. So I just canceled off one factor of M1 plus M2. So because it's not an elastic collision, the final kinetic energy is not equal to the initial kinetic energy. So we can actually compute the change in kinetic energy. So, I mean, some energy should be lost, right? So, so let's compute it. So it's going to be the initial kinetic energy minus the final kinetic energy. And putting in our expressions. V1 squared. So that was the initial one. And then if you look here, we've got this factor of M1 over M1 plus M2. So this gave us the initial kinetic energy, and then we have this extra factor of M1 over M1 plus M2 for the final kinetic energy. So if I rearrange this, so let's just do the arithmetic out. M1 V1 squared. Get rid of 0. This is M1 plus M2 minus M1. So this cancels this. And it looks like this. C1I. So you guys should recognize this is the reduced mass. So, so what does that tell you? Well, the initial kinetic energy was some value, and then the final, for any system, kinetic energy can be written in terms of the center mass term plus a relative term. Because we let the particles stick together, we actually got rid of the relative term. So the change in the kinetic energy is equal to the relative kinetic energy. And you can see that because delta KE is equal to 1/2 mu VI V1I squared, and this is the relative velocity. So we can write delta KE is equal to 1/2 mu V squared. So the initial velocity of the first one is equal to the relative one because the second particle started at 0 velocity. So yeah, so we could have calculated it that way too. Just say if in the center of mass frame. So let's now think about this collision in the center of mass frame. In the center of mass frame, we've got this guy going in and that guy going in at a smaller velocity if it's more massive. And then after the collision, it's not moving because we're in the center of mass frame. So it's fixed. This is before, and this is after. And this is the same collision in the center of mass frame. which is another way of just saying the relative velocity between the two particles went to 0 because they stuck together. So not necessarily surprising. So these examples, what I'm trying to show you is it's just there's nothing inconsistent about working in either frame, and sometimes it gives you a little bit more insight about what's going on if you're in a preferred reference frame. So you can choose which reference frames you want to go into, and usually the center mass frame is useful. Not always, but usually it's a good choice. Okay, so this was all collisions in one dimension, right? So what about more dimensions? Okay, so let's think about non-relativistic collisions in 3D, for example. So momentum is always conserved. In these collisions. But now we've got 3 components. So each component is conserved. Separately, so you actually get 3 equations. So that's 3 equations. And if it's an elastic collision, so if it's elastic, then energy is conserved, or kinetic energy is conserved. So let's do an example. So an example would be disintegration. So I have to give an example here. So supposing I have some particle, so I'm talking about 2D, so I have an X and a Y axis. I'm going to take some particle M, and I'm going to give it a velocity in the horizontal direction of V. And then when it reaches the origin, which is right here, so this is before, when it reaches the origin, it disintegrates. And so we're going to wind up with 3 particles. So we have M1 going out that way. No, not M1, M2. M2 is going out this way at a velocity V2. And we're going to give M1 let's do this. M1 is going out at V1, and then YX. And then there's going to be a 3rd particle going this way that we might not be able to see, and that's M3, and it's going out at a velocity V3. And there's this angle theta here. So supposing we detect M2 and V2 and M1 and V2 and V1, and we want to find out what's V3 and what's theta. So using conservation of momentum, we ought to be able to find these. So to make things a little bit easier, we'll assume that no mass is lost. So M3 is equal to M minus M1 plus M2. So we're going to assume that's true. Oops, there's a minus sign. So that just means M1 plus M2 plus M3 is equal to big M, which was the initial mass of the incoming particle. Okay, so let's draw. Well, I really need to keep this picture here because it helps. So let's get rid of some of this and do it up on the top. So let's use the fact that momentum is conserved. So momentum in the X direction the initial momentum. So momentum in the x direction, the initial momentum is mv, because this particle here moves horizontally. And the final momentum, so m1 doesn't contribute to the x component of momentum. Right. So if I adopt v2 as being positive, then it's going to be minus m2 v2. And then I have the horizontal component of m3 and v3. And according to theta, I'd get a cosine theta term. So this is the horizontal component of momentum. And I just related the initial momentum to the final momentum. So now what about the vertical component? So the vertical component, we have m0 because the initial particle did not have any. The momentum, the velocity component in the vertical direction is 0. But m1 has a vertical component of momentum. And m3 does too. So we'll take it in the minus direction, assuming v3 is positive. Sine theta. So this is the vertical component of momentum. Okay, so it's handy to write these and move the cosines and sine terms onto the same side of the equation. So we can write like this, rewrite these equations like this. M3 V3 sine theta is equal to M1 V1. And so I can compute the square of both of these equations and add them together. And then cosine squared plus sine squared equals 1. And so that means M3 V3 squared is equal to M2 V2 plus MV squared plus M1 V1 squared. And I can take the square root of both sides. To actually solve for V3. These are squares, squared, squared, squared. Okay, so we found V3. Let's just erase this. And now I can take the ratio of these two equations here. M3 V3. Oh, the M3 V3s cancel actually. So let's take this one divided by that one. Tan theta is equal to M1 V1 divided by M2 V2 plus MV. And that will let me solve for theta. And actually, if you want to make sure that you get factors of, get the signs right, you can use the ATAN2 version of this. And so we found the angle and we found the velocity. So in this, so what do we didn't use any energy constraint in this particular problem. We used the fact that we had a lot of information post collision, meaning we measured we could measure the masses M1 and M2, and so we assumed we knew the masses of the two of the final particles, and we assumed that we knew the directions and velocities of two of the particles. And so momentum conservation was enough to find out about a mysterious third particle, like where did it go in this problem. And so this kind of like gives you a feeling for what, many particle physics experiments are about. So they don't always detect all the particles coming out of an interaction, but they infer what could have happened based on the particles they do detect. And they use, things like momentum conservation and energy conservation to do that. And they keep track of a lot of particles and a lot of timing for when events happen and trace back to figure out when things disintegrated or interacted. So, this is a really simplified version of that, but, it's kind of a heart of a bunch of particles, a lot of different types of particle physics experiments. Okay, so moving on. So now let's talk about relativistic collisions or reactions. So that last one is disintegration. You can think of that. You can also think about that as a reaction. So relativistic collisions. So a bunch of particles. So because we're working with relativistic setting, we have a total energy and we have a total momentum. So these are totals. And so what do I mean by total? E is going to be the sum of all the energies of each particle, and momentum is going to be the sum of the momenta of each particle. And in this case, EI will be gamma I m I c squared. That's our formula for total energy in the relativistic setting, including rest energy, and momenta for each particle is equal to gamma I m I vi. So these are our special relativistic versions. So so this is total energy. In the collision, the total energy should be conserved during the collision, and the total momentum should be conserved. And that means the sums for the initial. So wait, let's write that a little bit more clearly. So these are, for each particle, we have initial energies, is going to be the sum for each particle, the final energy. And likewise, the same thing is true for the momenta. Final. So here, I doesn't refer to initial, it refers to the index of each particle. So this is another way of saying energy and momentum are conserved. You may not necessarily have the same number of particles before and after. Yeah, things might combine. So again, what reference frame do you work in? So it can be convenient to find the center of mass reference frame, but instead of just subtracting a velocity, you have to do a Lorentz transformation to go into the center of mass reference frame. So you can always find a velocity that gives you a zero momentum. So in the special relativity setting, what is the center of mass frame? It's a frame that gives you zero total momentum. And you can always find a velocity that does that. But in order to transfer between reference frames, you have to use a Lorentz transformation. So it's a little bit more complicated than just subtracting the center of mass velocity to go into the center of mass frame. So I don't think we have any problems asking you to do Lorentz transformations because we haven't talked about them, but you'll practice this up later in your physics sequence. You'll learn how to do Lorentz transformations. So let's do an example. So yeah, let's do an absorption of a photon. A photon. So so start with a particle. So M, that's rest mass M, and we've got a photon coming in. This is a photon. and it has energy E gamma. And so that's before. And then after, we have a particle. And so the photon, if this is fixed, so this is at rest. If we add the momentum, so remember the momentum of a photon is the energy divided by C. The momentum of a photon is E gamma divided by C. So the total momentum before is not zero. And so that means this thing has to be moving after. But we also need to conserve energy. And so what that essentially, so the energy of this system is the rest mass of this particle, because it's at zero velocity, plus the energy of the momentum. So we have actually extra energy. And what that means is this has to have a slightly higher rest mass. It has to be different. So let's figure out what it would have to be. So the total momentum is the momentum of the photon divided by C, the energy of the photon divided by C, because the momentum of our particle at rest is zero. And this has to equal the total final momentum. And the total final momentum has to equal gamma final M final C squared. Oh, no, not C squared. What am I doing? V final, right? So this is the total momentum. And this is the initial. And this is the final. So this has to hold. So the energy, the total energy, the initial energy is the energy of the photon plus the rest mass of the particle. And this, so this is initial. And the final energy, since we only have one particle, is going to look like this. C squared. Okay, good. So so I can take so now our goal is to figure out what we have two unknowns, we have two equations here. Our goal is to figure out what the velocity of the particle afterwards and the rest mass of the particle afterwards. So yeah, so I can take the ratio of these two things. So the left-hand side, look, I know this I know, and this I know down here. So I can take the ratio of these two things. If I do that, then I can solve for the final velocity. And so if I do that, I get this P final. What, that doesn't make sense. Yeah, well, let's just take the ratio of these two guys. Then everything cancels out except we have, oh, yeah. Let's just take the ratio of these two guys. Then we get VF over, let's erase this and do this again. So we have VF over C squared is equal to PF over E gamma plus MC squared. And then I can move this C squared onto the other side. And I get that. And now I can replace PF with E gamma over C. So it's E gamma C over E gamma plus MC squared. So now we know the final velocity. And since we know the final velocity, we can compute gamma f, and then we can put that in here, and then use the fact that this, the E gamma plus MC squared is equal to gamma f MF MC squared to solve for MF. So once we have BF, solving for MF is not that hard. So I'm just going to write down the answer here. It's a little bit of arithmetic, nothing too hard. 2E gamma over MC squared plus 1. So that's this, and that's that. So, so that illustrates, an encounter and how you solve for what happened afterwards based on what you found initially, and also illustrated using, energy and momentum of photons. It's like particles. Okay, so I think I'm out of view boards, so I'm gonna go out and back in again so that we have a nice fresh set of 12 boards, whiteboards. Okay, so let's look and see what time it is. Oh, okay, we're doing good. We have some time. So let's talk about a couple other reactions. Yeah, let's talk about a couple other reactions. So let's talk about electron positron annihilation. So electron positron annihilation, you have a positron comes in and an electron comes in, and out comes 2 photons. Oops. They have to be anti-aligned, otherwise momentum isn't conserved. So for this particular, you can write this reaction like this. So this is the electron, that's the positron. They have the same rest mass, but the opposite charge. So the initial electron and positron rest mass is this. And so the initial energy is this. That's the rest mass, but you could have some extra if they, because they have some kinetic energy. So energy is probably bigger than this. So the smallest the energy could be is if they're moving really slowly, then the energy would be this. And then, so that has to equal twice the energies of the photons. So the rest mass of an electron, people usually write this in terms of keV, it's 511 keV. And that corresponds to a gamma ray. And yeah, so the gamma rays at 511 keV are in fact detected all over the galaxy, in fact. And so that actually tells you that there are pretty energetic things going on, meaning electrons and positrons, things energetic enough to make a whole bunch of positrons that can annihilate. So why can't, you can ask, why can't you make a single photon in this? Does anybody have an idea? So an electron positron come in and out come 2 photons. Why can't you have a single photon?
Conservation of momentum, maybe.
Yeah, exactly. Because think about it, go into the center mass frame, and because the electron and positron have the same mass, then the center mass frame, there's no momentum. But if I let a photon go, it has momentum. There's no way to zero out the momentum in the center of mass spring. So another way to think about that is, yeah, so that's basically right. There's no way to conserve momentum. So yeah. So you have to have two momentum. They can come out in any direction though. There's nothing saying that they have to come out in the same direction that the electrons came in at. They can go out at some other direction. Okay, so yeah, so that's electron-positron annihilation. And looking at the maps of the Milky Way are actually pretty interesting. There's a lot of them in the galactic center, and people talk about there's some sources, high energy sources that produce 511 keV gamma rays. People, there's a field of work on it. Segev's actually kind of involved in this. If you want more detail, ask Segev, because he actually works on stuff like this. Okay, so another set of experiments. So let's talk about the Rutherford gold foil experiment. So Rutherford. So when I was in school, I learned to call it the Rutherford gold foil experiment. But apparently it was done in Rutherford's lab. And the people who actually did the experiment were Geiger and Marsden. And so nowadays it's also known as the Geiger-Marsden experiments. So what is this famous experiment? So the experiment is you get this gold foil. And then you shine, you get a radioactive source. The radioactive source produces alpha particles. Source. So what are alpha particles? Alpha particles are just helium nuclei. So without the electrons. So they're pretty heavy. 2 electrons, 2 neutrons, 4 atomic mass units. And these alpha particles, so what do they do when they see the gold foil? Well, most of them just pass right through. So you put a detector on the backside of the gold foil. And the ones they pass, most of them just go right through as if there's nothing there. They don't even change direction. Some of them are scattered. And so you can measure this angle theta. And things can come backwards too. So theta could go all the way out here. So you can put detectors all around the gold foil. So most pass through undeflected. And a few are strongly deflected. So the interpretation is that the gold foil is mostly empty. Mostly empty space. And then the nuclei in the gold foil have to be really small and really compact. So since a gold nucleus is a lot more massive than an alpha particle, when the alpha particle hits, it's like really strongly deflected. So that explains, that's kind of the only way to explain the experiment. And so before that experiment, people kind of thought, matter might be uniformly, or nuclei might be kind of these soft, big things. But no, most of space is empty and the nuclei are super small. So this gold foil experiment, gave that picture and allowed an estimate for the size of atomic nuclei. So they're just small. Okay, one last experiment we're going to talk about, beta decay. So what's beta decay? So beta decay, you start off with a carbon atom. But it's carbon 14. So this thing down here is the number of protons. This number up here is the number of protons plus neutrons. So so we have carbon turns in, so carbon 14, which is unstable isotope of carbon, turns into a nitrogen nucleus. And when that happens, you get an electron and you get another thing, which was originally hard to figure out was there. So that's kind of the point of the beta decay experiment. So, so the number of things in the nucleus stays the same. So the total number of protons plus neutrons stays at 14. But we have one extra proton in the nitrogen compared to the carbon. So one neutron turns into a proton. So since proton is positive, in order to make charge balance, that's why you need the electron here, so that the sum of the charges is the same on either side of the reaction. Right, so that's where the electron comes from. So what about this thing? So nowadays we, in most theories, this involves, so an electron is a lepton, and you need to conserve lepton number when you have something that's involving the weak interaction. So what's supposed to be really going on during the reaction is that there's an intermediate virtual W- boson that mediates the interaction. And you need the anti-neutrino there so you conserve lepton numbers. So electron has lepton number 1, and it's an anti-neutrino, so that gives you -1. And since it involves an electron, you need an electron neutrino here. So this is, how we would qualitatively talk about this experiment now. But in the 1911 or so, what they were doing was looking at beta decay, so you could get carbon 14 and look at the electrons that came out of the reaction. And so they were looking at the spectrum of the electrons. So what's beta? Yeah, so alpha particle were helium nuclei, but beta particles are electrons. So radioactively emitted, when they're radioactively emitted, they called them beta particles. So they were looking at the distribution of the beta particles, or the electrons, and they were having trouble reconciling the energy, like conservation of energy is an issue. So so it happened, and so there two different experiments, one by Lisa Meitner and Otto Hahn, and the other by Jean Danes around 1912. And the distribution of the energies was an apparent contradiction to conservation of energy. So so there are a bunch of proposals how to resolve this. So Wolfgang Pauli suggested that there was another particle involved in the reaction that they were not detecting. And so what kinds of particles are hard to detect? Things that are neutral, so they don't have charge. So he proposed that there was a light neutral particle that came out of the reaction, and he called it the neutron. But there was, in 1932, a different particle was also called a neutron, and it was massive. And in this one, they needed a low mass particle to explain the energy distribution. So so Fermi renamed Pauli's neutron as the neutrino. And And it took many years later. So it was proposed as to explain this problem. And it took many years before, it was possible to actually more rigorously detect, because neutrinos don't interact very strongly with regular matter. So that's why it's called the weak interaction. So, so there were other experiments that indirectly inferred the existence of neutrinos. So neutrino physics is actually a pretty active area of particle physics now. And recently, they've discovered that neutrinos probably have a little bit of mass, and the different kinds of neutrinos actually turn into each other. They oscillate back and forth. So neutrino physics is still pretty interesting field. Okay, so let's summarize what we talked about today, because I think we're kind of running out of time, but let me summarize. So we wrote down, why is there a problem with conservation of energy? Okay, yeah, so special relativity, we assume energy is conserved and momentum is conserved. And so if you have a reaction and the total energies before and after are not the same, then that would violate special relativity, where the total energy is conserved. So that's why. Yeah, so actually one more thing to mention. So EP, when I write this out like this, there's no mass energy duality. Well, yeah, so when we wrote down energy, you could write in the limit of no velocity, you get a rest mass. So you could call that energy mass. I'm not sure what you mean by energy mass duality here, but our relativistic form for energy never goes, it doesn't go to zero if you have a massless particle. You always have the rest mass at the minimum in any frame that you're in, any Lorentz frame. In any case, so let me just make a quick comment here. So we have energy and momentum here. We can also write time and position. And so if you write things out like this, so think of a vector t, x, y, z. And I can write this as a vector px, py, pz. So if I write things out like this, these are 4 vectors. And space-time is, oh, wait, so the question was, does the nitrogen change mass? Yeah, so electrons and protons are slightly different masses, and when they get combined in a nucleus, the energy is also not just the sum. So there's more complicated nuclear physics trying to account for exactly the mass of a nucleus. But you can measure the mass of a nitrogen atom, and you can measure the mass of a carbon atom. So these are things that they knew how to measure already. So this is why they were good at, they knew enough about carbon and nitrogen isotopes to actually rigorously say we have a problem with conservation of energy. So that's kind of the point of that. But I have to admit, I haven't actually ever gone through Lise Meitner's calculations. So, if you're interested, maybe we should look more detailed. In any case, so let me finish making the point. So normally when we're thinking about Euclidean space or non-relativistic setting, we have space and we have time. In special relativity, we have space-time, and it's a 4-dimensional thing. And so when you write down energy and momentum, we can think of this as a 4-vector, and we can think of this as a 4-vector. So time and space, both of these are 4 vectors. And what you'll find out in special relativity is that there's a way to define the length of a 4-vector, and it's a conserved quantity conserve quantity in the sense that if you do a Lorentz transformation, you don't affect the length of the vector. So, so energy turns into momentum, and momentum turns into energy if you do a Lorentz transformation, and time gets mixed with space if you do a Lorentz transformation. And the Lorentz transformations are designed to make it so the speed of light is the same in all reference frames. So it's just another way to think about it. So a consequence of special relativity is that energy and momentum are coupled, time and space are coupled. But in any case, so let's review what we kind of covered in this lecture. We talked about how to compute final velocities for non-relativistic collisions used from the initial velocities. And these were, collisions between two particles in with 1 degree of freedom. And we wrote down some formulas if the second particle was initially fixed in the lab frame. We redid the same calculation in the center of mass frame, showed you get the same result. But the collision looks much more simple in the center of mass frame. If it's an elastic collision, the velocities just flip sign. And if it's an inelastic collision, the velocities just drop to 0. So in some sense, it's easier to do those. You could think about doing those calculations in the center of mass frame, might save you some time. It's at the cost of transferring in and out of the center of mass frame. So one thing I would like you guys to learn how to do is transfer in and out of center of mass frame. So how to. So I showed you how to do that for a non-relativistic setting. In the relativistic setting, it's a little bit more complicated because you have to use Lorentz transformation. So yeah, so this is something we learn how to do. Then for elastic collisions, the kinetic energy is conserved. For all collisions, these are non-relativistic. Momentum is conserved. Actually, all collisions, not non-relativistic. Momentum is conserved. And if we have relativistic collisions, E and P are conserved. So I think that kind of summarizes what we've done in this section. And I think we're pretty much done with class. So we'll end there. Sure. Any questions?